Notice you have seen that before and this. These are all the formulae required for this section of CSEC, but we have already covered these in the last video. And now we will move on to the remaining 4 formulae in this section. These 4. We begin with number 5. R total is equal to R1 plus R2 plus R3 and so on. This formula is used to find the effective resistance of 2 or more resistors in series. RT is the sum of the resistors, while R1, R2, R3, and so on are the individual resistors that are in this series. So let's look at a very simple example. Calculate the effective or total resistance of 3 resistors, 10 ohms, 20 ohms, and 30 ohms that are in series to one another. Well, we know that R total is equal to R1 plus R2 plus R3. Therefore, we just substitute the numbers we are given and we get the total resistance is 60 ohms. We can say 60 plus or minus 5 ohms since we are rounding off at this position, the tens position where the 6 is, and that is our uncertain digit. So we'll take half of the tens position and that will give us plus or minus 5. If we look at another example, we have 30 ohms, 20 ohms, and 40 ohms in series. There is an ammeter here, switch here, switch, battery, 12 volt, and the rest of the circuit. Example 2, part A. Calculate the effective or total resistance of the 3 resistors shown in the diagram above. Well, we know R1 is 30 ohms, R2 is 20 ohms, R3 is 40 ohms. We want to find R total. R total is equal to R1 plus R2 plus R3. So we simply add them and we get 90 ohms if we want to show our margin of error. Since this is our uncertain digit, half of that position is 5, and the answer is 90 plus or minus 5 ohms. That is the total resistance of these 3 resistors up here in series. Now we found that the resistance is 90 ohms. In this question, you may also be asked to calculate the current at A, which is here, that ammeter, when the switch is switched on. So let's see what we know. We can treat all of those as one resistor of 90 ohms. So our resistance is 90 ohms. The potential difference or voltage is 12 volts. We want to find current. We know that V is equal to IR. Therefore, I is equal to V over R. We substitute the numbers we are given and we get the current of 0.133 amp. But you know you cannot leave it like that. You have too many significant figures. This has 2 significant figures. This has 1 significant figure. So our answer can only have 1 significant figure. So we have to round off here and we get 0.1 amp. Since we are rounding off at this 1/10 position, we can easily add plus or minus 0.05 amp. So formula 5 we find the total resistance of resistors in series. You simply add them up. Now we come to formula 6. This formula is used to find the effective or total resistance of two or more resistors in parallel. Let's arrange those three resistors we had in the previous question from series to parallel. So they will look like this: 30 ohm, 20 ohm, 40 ohms. Put in the rest of the circuit, including the battery. Now, part A, calculate the total effective resistance of the three resistors shown in the diagram above. Now, if these were in series, we will just simply add them up, but they are in parallel. So we have to use this formula here. We know that R1 is 30 ohms, R2 is 20 ohms, R3 is 40 ohms. We want to find R total. The formula is 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So now we substitute where R1 is, we put in 30, and so on. We can do that in our calculator, but I am just going to explain how we come up with the next line. If you actually had to add 1 over 30 plus 1 over 20 plus 1 over 40, find an LCM of 120. 30 into 120 is 4, 4 ones 4, and so on. And so you get 13 over 120. But remember, that is not the total resistance. That is 1 over the total resistance. So we have 1 over R total is equal to 13 over 120. We invert both sides of the equation, and we get R total is equal to 120 over 13. We work that out, and we get 9.2308 ohms. That has too many significant figures. Our answer can only have one significant figure, so we have to round off there, and we get 9 ohms. And that should be enough for CSEC. However, you could always write the uncertainty. Since we are rounding off at the ones position, half of that will be 0.5. So that we can better write our answer as 9 plus or minus 0.5 ohms. But this should suffice for CSEC. So we calculated the total resistance, and we came up with 9 ohms for those three resistors in parallel. Note that the effective resistance of resistors in parallel is always less than the least of the parallel resistors. So the three resistors we have here are 30 ohms, 20 ohms, and 40 ohms. What did we get as their effective resistance, their total resistance? 9 ohms. 9 is less than the least of these. So we calculated the resistance, 9 ohms. Part B, in this question, you may also be asked to calculate the current at A when S1 is switched on. When the switch is closed, what is the current flowing through this circuit? As I said, we could treat all of those as one resistor, which is now 9.2 ohms. We will use 9.2 and not 9. We don't want to round off too early. So we get the total resistance, 9.2 ohms. The potential difference is 12 volts. We want to find the current. V is equal to IR. If we set I as the subject of the formula, I is equal to V over R. Substitute the numbers we are given, and we get a current of 1.304 amp. Now we have two significant figures here and 2, so our answer can only have 2 significant figures. We have to round off where that 3 is, and so we get a current of 1.3 amp, and that should be good enough for CSEC. But you know, you can always write in a margin of error like this. So let's look at another example, this time with only two resistors in parallel, just two. Now, this formula up here, formula 6, is used to find the effective or total resistance of two or more resistors in parallel, as we just saw in the last slide. So let's do this with two, one way, and then there is a shortcut with just two resistors. So we know that R1 is 30 ohms, R2 is 20 ohms. We want to find R total. We know 1 over R total is equal to 1 over R1 plus 1 over R2. We substitute the numbers we get, and we eventually come up with 12 ohms. Remember, you have to invert both sides of the equation after this point. Now, if you have only two resistors, there is a shortcut, and you don't have to go through this process here. There is a shortcut. So let's look at the shortcut. If we were to add 1 over R1 plus 1 over R2, we get an LCM, which is R1, R2. R1 into R1, R2 would be R2, which is this. And of course, that plus is there. And this is R1. But remember, that is 1 over R total. If you invert both sides of that equation, you will get R total is equal to R1 multiplied by R2 over R1 plus R2. And this is a shortcut if you have only two resistors. The total resistance is the product of the two resistors divided by their sum. And if we were to do that with these two numbers that we have over here, we will get 20 multiplied by 30 divided by 20 plus 30. That would be 600 divided by 50, and we will get back the same 12. Now remember, this only works for two resistors. You can use this method over here for two resistors, or you could use the shortcut method over here. Once you have three resistors, then you have to use the full formula. 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Note again, the total or effective resistance of resistors in parallel is always less than the least of the parallel resistors. So, to reinforce that concept, if you have these resistors in parallel, 20 ohms, 5 ohms, 40 ohms, 50 ohms, and 30 ohms, you know straight off that their sum or their total or their effective resistance must be less than 5 ohms, which is the least of the resistors here. So let us say we have these two resistors in parallel, and you have this one over here in series to these two that are in parallel. We finish the rest of the circuit. Ammeter is here. Another ammeter is there. A voltmeter is across this resistor, 40 ohms. And a voltmeter is across these two resistors in parallel, V2. So the first part of the question says, calculate the total, which is the effective resistance of the three resistors shown in the diagram above. So what we will have to do, calculate these two that are in parallel, then treat those two as one that is in series with this one over here. So R1 is 30 ohms, R2 is 20 ohms. R1 plus R2, remember we have only two resistors here, so we will take their product and divide it by their sum, and we get 12 ohms. That's these two here work out the 12 ohms. So we could replace them and say 12 ohms. You have 12 ohms in series with 40 ohms. And that would mean we would add the 40 to the 12, and we will get 52 ohms total resistance. That's the first part of the question. Second part of the question says, calculate the current at A1 when the switch S1 is closed. So we know that the total resistance in this circuit is 52 ohms. We know that the potential difference is 12 volts. We want to find I. We know that V is equal to IR. Therefore, I is equal to V over R. We substitute the numbers we have, and we get 0.23 amp. And that should suffice for CSEC. We have the correct number of significant figures. Part C of this same question is calculate the potential difference at V1 when the switch is closed. That is the potential difference across this resistor. So what do we know about this resistor? Well, we know that its resistance is 40 ohms. We know the current that flows through here, the main current, is 0.23 amp, which we just calculated up here, and we want to find V1. V1 is equal to IR3, and we substitute the numbers we are given, and we get 9.2 volts, and we can round that off to 9 volts since we are dealing with one significant figure here. So far, we have calculated the total resistance. We have calculated the total current, that's the current at A1. We have calculated the voltage at V1 here, the potential difference at V1 as 9 volts. We also need to calculate the potential difference at V2. That is this potential difference here. We know that V1 is 9.2 volts. We know that the EMF, the total voltage of this whole system, is 12 volts. This 12 volt here has to be split between that V1 and that V2. And since we already know that V1 is 9.2 volts, all we have to do is subtract it from 12. So V2 would be 12 volts minus 9.2 volts, and we get 2.8 volts, or we can round that off to 3 volts. Potential difference across this resistor is 9 volts, and across those two together is 3 volts. That would add up to 12 volts. Now, we are not finished yet. There is a part E. Find the current at A2. So we want to find a current here. We know the current that goes through here. We know that current as 0.23 amp. But that current comes here and it splits in two. Part of it goes that way and part comes this way. Now, if these two resistors were the same, then one half of the current will go to the top and one half below. But this one here is 20 and that one is 30. Now, the one that has the lower resistance would have more current. The higher resistance would have less current. So let's see how this goes. We know R1 is 30 ohms. We know that V2, that's the voltage across both of these, is the same voltage for parallel components. V is equal to IR. I is equal to V over R. We substitute the numbers we are given and we get 0.09 amp. So up here, out of that 0.23 amp, 0.09 amp goes up here, and of course the rest comes down here. There is an easier way of doing this part E that we just did, where you know the current that comes here, part of it goes there and part comes down here. we can use ratio. If we split that current into a 20 to 30 ratio, 20 to 30 ratio, which is the same as the 2 to 3 ratio, with A2, which is the current that goes through R1, getting the smaller share or portion, since it has a higher resistance, then it simply becomes A2 is equal to A1 multiplied by 2 over 5, not 3 over 5. And if you do that, you will get the same 0.09 amp. So there are two ways of doing that. You are allowed to use a scientific calculator like this. It is non-programmable. What concerns us right now are these two buttons. This one here that says A, B/C, and this other one here that says X to the negative 1. That one is inverse. This one is fraction. 30 ohms. This one is 20 ohms, and this one is 40 ohms. In this circuit, if we close this switch, this is 12 volt DC, of course. So what is the effective resistance of these three resistors in parallel? Or you may say, what is the total resistance of these three resistors in parallel? Well, we know 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, anyone could be R1, R2, or R3. But we can let this one here be R1, that one R2. So we have 1 over R total is equal to 1 over 30 plus 1 over 20 plus 1 over 40. And so we get 1 over R total is equal to 13 over 20. So let's see how that is done. 1 fraction button, that's over 30 plus 1 fraction button again over 20 plus 1 over 40, and we press equal sign and we get 13 over 120, 13 over 120. But that is 1 over R total. If we invert both sides of this equation, then we get R total over 1, which is really R total, is equal to 120 over 13. So if we invert that, which is this x to the minus 1 button, we invert that, and we get 9 and 3 over 13. So this shows us the improper fraction. This shows us whole number part plus the proper fraction part. If we press this same button again, now what we get is 9.23. 9.23. We round that off to approximately 9 because we are using one significant figure. And if we want to include the uncertainty, since we are rounding off at the ones position, we take half of that ones position, which is 0.5, and our answer would be 9 plus or minus 0.5 ohms. Note, as I said before, that if you have resistors in parallel and you are finding their total or their effective resistance, that effective resistance will always be less than the least of those resistors in parallel. And of course, you have to show your working if you are doing this in a CSEC. So far, we have completed these two in this video. We have 2 more to go. E is equal to PT, which is equal to VIT. We have seen this before in thermal physics. E is energy in joules. P is power in watts. V is EMF or potential difference, or what we would normally call the voltage in volts. I is current in amperes, amp, and T is time in seconds. So let's look at two questions that we already did before in thermal physics. Example 1. Calculate how much heat energy was added to a beaker of water if a 65-watt immersion heater was used for 45 seconds, assuming no energy loss. All right, so we know the power, we know the time. We want to find the energy. E is equal to PT. Substitute the numbers we are given. We get this. This has too many significant figures. We are only allowed 2 significant figures. So we have to round off here. And we can write 2,900 joules. That should be sufficient for CSEC. However, if you want to make doubly sure, you could add the error of margin. Since we are rounding off at the hundredths position, we take half of that position, which would be 50, and this is a better way of representing that answer. But this one up here, this one here, should suffice for CSEC. Example 2, which we already saw. Calculate how much heat energy was added to a beaker of water if a 24-volt immersion heater that draws 2.5 amp was used for 45 seconds. Now, in that previous one, we use E is equal to PT. Now, we are going to use E is equal to VIT. So what do we know? We know the voltage or the potential difference. We know the current. We know the time. We want to find the energy. E is equal to VIT. Just substitute the numbers we are given, and it so happens that we get exactly 2,700 joules. So we have the exact number of significant figures. We can, of course, take half of that hundredths position and add this part if we are not comfortable with just leaving our answer like that. But that answer is sufficient for CSEC. We look at example 3, still dealing with formula 7. E is equal to PT, which is equal to VIT. So what are we given? We are given the energy this time. It is in kilojoules, so we will carry it to joules. Remember, we said energy in this formula is in joules. Power is in kilowatts, 1.2 kilowatts. So we will carry it to watts, 1200 watts. We want to find the time. E is equal to PT. Therefore, T is equal to E over P. We substitute the numbers we are given, and we get this. You know that has too many significant figures. This has 3, this has 2. So our answer can only have 2 significant figures. We have to round off at the position where that 8 is. And so we get 380 seconds. And that should suffice for CSEC. But as usual, you can always write in the margin of error. Since we are rounding off at the tens position, our margin of error will be half of 10, which will be plus or minus 5. And this is a better way to represent our answer. But this answer up here should be sufficient for CSEC. So let's look at one more example like this in the use of formula 7. In a science experiment, Sally wants to add 2.5 kilojoules of energy to a lead block using an electrical method. She can preset the potential difference, the voltage, the current, and the timer. If the current is preset to 2.3 amp and the timer to 145 seconds, what must the potential difference be set at? So we are given the energy in joules, current in amp, time in seconds. We want to find V. E is equal to VIT. Change the subject of the formula to V, and we get V is equal to E over IT. Substitute the numbers we are given, and we get 7.496 volts. Now be very careful when you are using your calculator here. Notice the use of this parenthesis here. Be very careful. Your calculator should have those brackets. So it's 2,500 divided by open bracket 145 multiplied by 2.3 close bracket. If you don't use a bracket, this actually becomes 2,500 divided by 145 divide by 2.3 if you don't use the brackets, parentheses. Now, of course, this has too many significant figures. We have two significant figures here, 3 here, and 2 here. Our answer can only have two significant figures. We have to round off there. And so we get 7.5 volts. That should suffice for CSEC. As I said, you could always write in your margin of error. Since we are rounding off at the 0.1 position, we take half of that, which would be 0.05. So if E is equal to 2.5 kilojoules, which is 2,500 joules, I, which is the current, is 2.3 amp, and T is the time 145 seconds, and you want to find V, we know that E is equal to VIT. If we make V the subject of the formula, we will get E over IT. When we substitute our numbers that we are given, we get V is equal to 2,500 joules divided by 145 seconds multiplied by 2.3 amps. And here is where some students make a common error. You are dividing that number at the top there, the numerator, by the product of these two numbers below. So what you need to do, according to your calculator, you get 2,500 divide by open bracket 145 multiplied by 2.3 close bracket equal, and this is what we get, 7.496. So that is 7.496 volts, and we can round that off to 7.5. That is if your calculator has brackets. Now, if your calculator does not have bracket, you will have to do it this way. 2,500 divide by 145. Watch this, please. See, there's a multiplication here. In this context, it actually means divide, because you are dividing that number by this and this. So you divide by 2.3 equal, and you get back the same 7.496. So you could do it that way with the bracket, where the multiplication really means multiplication here. You could do it this way without the bracket, where that multiplication actually means division. But you are not to do this. 2,500 divide by 145 multiply by 2.3. No, not to do that. So let's see what happens if we were to do that. 2,500 divide by 145 multiply by 2.3, and we hit equal, and we get 39.655. 39.655 equal 39.655 volt. And of course, this is wrong. These two are correct. So be careful of this kind of a math that you do, where that multiplication means multiplication only if you are using a bracket here. If you are not using bracket, that multiplication is actually a division. So those four were done in the last video, those four. We just completed these three, and now we have this last one to deal with at this point. P is equal to I squared R. Now, this formula is used to calculate energy loss in transmission power cables, like the overhead electric lines that you see all the time. It is derived by substituting formula 2, V is equal to IR. In formula 3, P is equal to VI. So you take out that V from there and you put in the IR. And so we get P is equal to I squared R. P is power in watts, I is current in amperes, R is resistance of the transmission cables in ohms. Example 1. Calculate the power loss in transmission cables if its current is 15 amps and its total resistance is 23 ohms. So we know the current, we know the resistance, we want to find the power loss in cables. Now, do not mix up this power here with that power there. All right, so power loss in cables. P is equal to I squared R. Substitute the numbers we are given, and we get 5,175 watts. We have too many significant figures in this answer. That has two significant figures. That has two. So our answer can only have two significant figures. We have to round off at that hundredths position where the 1 is, and we get 5,200 watts. We can state that as 5.2 kilowatts, and this here better shows our rounding off. However, we can also add a 0.05 because we are taking half of that position. But this answer here, this one here, 5,200 watts, is sufficient for CSEC. Example 2. If you want to keep the power loss to no more than 8.9 kilowatts in transmission cables that have resistance of 85 ohms, what will be the maximum current? So we know the power loss, 8,900 watts. We know the total resistance, 85 ohms. We want to find I. P is equal to I squared R. Make I the subject of the formula, which is equal to the square root of P over R. Substitute the numbers we are given, and we get 10.2326 amps. Obviously, we have too many significant figures here. To begin with, we have two significant figures there and two here. Our answer can only have two significant figures, so we will need to round off where that 0 is, which is the 1's position, and we get 10 ohms. Now, this one could be a bit ambiguous, so just to make sure, we will add in the margin of error to show where our uncertain digit is. And since we are rounding off at the 1's position, we take half of that position, which would give us 0.5, and our answer can be clearly stated as 10 plus or minus 0.5 amp, which means we were rounding off at that position. And that brings us to the end of the formulae for this section, section D, electricity and magnetism. Notice we didn't do much on magnetism. Next, we come to the last section of the syllabus, and that is section E, the physics of the atom, where we'll be talking about nuclear reactions and atomic structure and so on. And this brings us to the end of video physics 19.